So, dear students, in previous video lectures, we have studied the different concepts of linearity because I started quantum mechanics by the initial concept of linearity. So now today we have lecture 1.3. In this lecture, the most important thing is that as you know better, like for example, in the previous video we studied about the Maxwell's theory, and the Maxwell's theory is actually a completely linear theory, means that satisfies the linearity property. But in the other hand, if we look at the Einstein's theory of relativity, that is completely non-linear, mean that is too much difficult to be handled over. So now today we are going to study that either the classical theory, means the classical physics is linear or non-linear, and on the other hand we have to study other case, means quantum mechanics or the quantum theory is either linear or that is non-linear. So now we will be having, my lecture outline is that I will be having the 2 points. The first point is claim number 1. I am claiming that classical mechanics, means classical theories are actually non-linear. And claim number 2, this will be my second point. Claim number 2, our case, means the quantum mechanics are the quantum theories that are actually completely linear, means so simple. And on third point, I will draw a conclusion remarks between claim 1 and claim 2, and then we will see that what does actually the linearity means and what does actually the non-linearity mean what is the significance of linearity and what is the significance of non-linearity and what will be their advantage. So let's have a start with claim 1. So today we have claim number 1. My claim is that classical theories, means the classical physics, the Newtonian physics is actually non-linear. So therefore claim number 1 is classical physics is non-linear. Classical physics is non-linear. Now the question is that how the classical mechanics is non-linear. Now we will be having the verification for this. For claim 1 we have the verification. So dear students, consider the case of particle in one dimension. Motion of particle in one dimension. Like for example, we have the easiest case, v of x. What is v of x? This is actually a particle in a potential, means particle moving in one dimension under the influence of potential v of x. And the next one we have for this x of t. This x of t is actually the dynamical variable. The dynamical variable, as I told in the previous lectures, this is the dynamical variable. Now we have equation for the dynamical variable, and that is m d square x of t divided by dt square is equal to mass times, actually we have the derivative, mass times the second derivative of position. The second derivative of position means actually the acceleration. This is equal to minus v prime of x of t. Now what is v prime? V prime is actually the derivative of v with respect to given argument. V prime of x of t is actually derivative of v with with respect to argument. So this is with respect to argument. Now we have the dynamical variable, and this is actually the equation for dynamical variable. You know better that it is actually mass times acceleration, which gives us the force according to the Newton's second law of motion, as we are considering the Newton law, because we are studying about the classical physics, the Newtonian physics. So now, my dear students, as we know here about the potential here is, I will explain but not that much. Now, this is actually a potential. In this potential here, this potential shows actually the positive values. This shows the positive values. Here is a mass. Here is a mass which tends towards right. It is a mass which tends towards left. So hence this mass tends towards the left. So therefore the potential is in the negative. So this is a bit explanation about this. Now, my dear students, the main thing is we should interpret this equation. Why? Because I have to verify this claim. So now we will be having the interpretation. Interpretation is in essence, now if you look here, means interpretation on the basis of linearity, either that is linear or non-linear. Here you have at this side the second order derivative of x. This is a linear. Why it is linear? Like for example d by dt, and the same is the case d by dt, x of t. Now you know, if we have d by dt and d by dt on the basis on applying the linearity property, means if we have some property of linearity, then you have to apply derivative on the first function, then derivative on the second function, then the second derivative on the first function, then the second derivative on the second function. So it means that is the simple way to analyze, and it obeys the property of linearity, either that is the sum property or the product property. So therefore this side in this side, this term is actually linear. So this term is linear. On the other side, if we look about the potential may not be linear, because the potential may not be linear because actually the main reason is that the potential is arbitrary. Potential is arbitrary. Arbitrary means, like for example, if potential varies with x cube, so the derivative of potential goes like x square, and x square is not linear. So therefore this function is not linear. This is not linear because potential is actually arbitrary. So this is the main point. Now, the main thing is the conclusion about this verification. That what does it mean that it is not linear? Means the answer is not linear. So now we have conclusion. Dear students, the conclusion we have about this is that we received actually the non-linearity in the equation of Newton. Means we studied or we considered the case of particle in one dimension on the basis of Newton's law of motion. So therefore, my dear students, here we received the non-linearity, and hence the Newtonian or classical theories are actually the non-linear theories. Or that is the non-linear physics, you can call it. But now the question is, what does it mean that the classical physics or the Newtonian mechanics is non-linear? My dear students, actually it means that it does not satisfy the condition of linearity. That was actually, if, like for example, if we have two solutions, means x1 of t and x2 of t, the non-linearity means x1 of t and x2 of t, if these are the solution of an equation, then their superposition means their sum may not be the solution. We cannot guarantee that their sum is a solution. That is actually mean that this is non-linear. Or you can say that it does not satisfy that property of sum and product. That was v prime. Like for example, if you have two functions, v prime u plus v. So this is not equal to v prime of u plus v prime of v. Or you can say, like for example, it does not satisfy the property of the product. Like we were having the constant here, and here is the unknown function. So this is not equal to the alpha v prime of u. This is the physical meaning that why classical mechanics is the non-linear. So this was my claim number 1. In this claim we studied that actually the classical physics is non-linear, means it is too much difficult to analyze. Like for example, we have many body problems. In 2 dimension you can solve it easily, but in 3 dimension Newton didn't solve. That is too much difficult and too much complicated. So that is why we call it the non-linear. So this is the main concept behind claim number 1. Now we will be having claim 2. So let's come towards claim 2. I hope that it will be clear for you. Now claim number 2. In claim 2, I claimed at the start of this lecture that quantum mechanics is actually linear. Our quantum theories are actually linear. So quantum mechanics is linear. Now for this we have the verification. How quantum mechanics is linear? Now we will be having actually the verification for this. The verification is, first we have to choose the dynamical variable. The dynamical variable here I have to choose is psi. This is a dynamical variable. This dynamical variable is called wave function. Now, the most important question is that why we need the concept of wave function. Why we need the concept of wave function? This is the very basic question. Now, we need the concept of wave function in order to describe the dynamics of quantum systems. We need the concept of wave function to describe the dynamics of quantum systems. To describe the dynamics of quantum systems. And the value of wave function depends upon time and hence well position or something else. Now for the dynamical variable means the wave function, we have an equation, and that equation is actually given by the Schrödinger in 1925. So we will be having a Schrödinger equation. Schrödinger equation 1925. Now the Schrödinger equation is iota h cut partial over partial t psi is equal to h hat psi. Now this is the Schrödinger equation. Here we have h cut, or we call it h bar. And this is actually, we are differentiating the wave function with respect to time, and this is h. This h is, you can symbolize it, or you can read it as h cape or h hat. H hat या H cape means Hamiltonian. Hamiltonian. The Hamiltonian is always a linear function. This is actually linear. And here is the psi eta h cut. Inshallah, we will study the Schrödinger equation in very detail, but only now I have to verify my claim. For that, I choose the Schrödinger equation on the basis of the dynamical variable. Now, if you look to this side, in this side, now I have actually the interpretation. I should write here. Interpretation. Now, if you look at this side, this term is actually naturally linear. This is naturally linear. Naturally linear means that this is the first order derivative, the simple derivative. And here h is already linear. So it means, now it is also linear and it is also linear. So that actually means that quantum mechanics is linear. But now the question is, what is the conclusion? Or you can call, what is the physical meaning that quantum mechanics is linear? My dear students, the physical meaning is, to the point, if psi 1 of t and psi 2 of t, if these are the two solutions, then their superposition will also be the solution. It is the very important point and it is the very beautiful concept in the quantum mechanics. If psi 1 and psi 2 are the solutions, then their superposition means their addition will also be a solution. So therefore, you will see that in the upcoming lectures, we always consider sometimes their sum is also a solution. That is actually mean that quantum mechanics is linear. And it satisfies, another meaning is, the quantum mechanics satisfies the linearity condition. That means, like for example, we have the two functions. If the two functions are added, then the operator may act individually in the simple way, and the same is the case for the product rule. So this is the very simple meaning of the quantum mechanics linearity. Now, at the end, now the question is, how can we compare it? But before that, I want to say something about this. That, like for example, if I want to write it on the basis of linearity, you can, if you wish to write, L psi is equal to 0. Now L psi is equal to 0 means that actually, like for example, here we have alpha h cut partial psi over partial t minus h hat psi is equal to 0. So now the question is that what does L psi means? Yeah, what is L psi? So this we have to clarify. This is actually meant by the L psi. Now I told this is linear, so the quantum mechanics is a linear. This is only the simple case, and how we can define L, this function is actually equal to the L, means this is actually L, like this. Now the most important question is that what is the conclusion remarks or the concluding remarks for claim 1 and claim 2. What does claim 1 and claim 2 actually means? So now the last point we have, conclusion remarks. The conclusion remarks is that quantum mechanics is linear and classical mechanics is non-linear. It means the quantum mechanics is simple than classical mechanics. How that is simple? Here I verified by claim 1 and claim 2. The quantum mechanics is actually very simple. you will see in the upcoming lecture as well, throughout our lecture you will see that in the quantum mechanics you will be having the very simple solutions. The quantum mechanics is simple. It is profoundly simple. And the classical mechanics is actually more complicated, or you can say like this. And another point is, in the classical physics, the linearity property does not hold, while in quantum mechanics, the linearity property holds. Means, in classical mechanics, if we are given with the two solutions, then their superposition may not be the solution. While in quantum mechanics, if we are given with two solutions, their sum or their superposition will also be the solution. So that is our today's lecture. In the upcoming lectures, we will describe that here alpha is the imaginary or complex number. So we will describe that what is the necessity of complex number in the quantum mechanics. So see you in the next lecture.